Chapter 12, Radiation. Now, before we understand what is radiative heat transfer, we need to know what is radiation and how is radiation caused. So all of us know that an atom constitutes of a nucleus in the center, which has neutrons and protons, and it has electrons that move around it in orbits. And based on what atom you have, you will have a different number of orbits and different number of electrons in them. And if these electrons are exposed to some uh, energy, that's the excitation energy, they will absorb that energy, and then they will move to an excited state. That means they'll jump to a orbit at a higher level, and as they decay from the higher orbital to a lower orbital, they will emit some radiation in the process. Now these electrons may jump to uh, a consecutive orbital, or they may skip orbitals and jump to three orbitals, so it depends. And the emission, that is the radiation that is emitted from them, depends on the atom and the energy that is being released uh, while these electrons decay from an excited state back to the ground state. So this is how a radiation occurs. Mostly it's at an atomic level, and the emission that occurs can occur in a wide range of frequencies and wavelengths, and the frequency is usually dependent on the amount of energy that is absorbed or released while the electron decays. So radiations are emitted at all wavelengths. So you can have radiations uh, from gamma rays up to microwaves, and they may be radiated by different means. So you may have gamma rays or X-rays being released when you have nuclear fission or fusion, whereas mostly thermal radiation falls or occurs, or the radiation between zero point 0.1 micrometer to 100 micrometers is referred to as thermal radiation, and that's the radiation that we'll consider as for the radiative heat transfer. And as you see, the visible spectrum just falls into the small black box, so it's a very small portion of the thermal radiation spectrum that is released, and most of the thermal radiation falls under the infrared regime. So most of the infrared radiations contribute to thermal heat transfer or thermal radiation. Okay, so moving on to radiative heat transfer. Let's say we have a body which has a surface temperature of Ts, and let's say it's located in a surrounding which is surrounded by vacuum, and the surrounding is at a temperature T surrounding. Okay, so uh, every body that has a finite temperature will emit radiation. So your body with temperature Ts will emit a radiation of Q rad comma S, and your surrounding, which is at a temperature T surrounding, will emit a radiation of Q rad surrounding. And because this radiation is in the form of electromagnetic waves, it does not require any material medium for heat transfer, unlike convection and conduction. So mostly radiative heat transfer does not require any material medium, and every object that has that is not at an absolute zero temperature will emit some radiation. So now let's say that in this case, if Ts is greater than T surrounding, that means the surface temperature of your body is greater than the surrounding temperature. And remember that in radiation, we'll assume that our surrounding temperature, oh, surrounding temperature is constant. Okay, so let's say if Ts is greater than T surrounding, what will this mean? This will mean that Ts uh, will radiate heat at a faster rate, or let me say this, that it will radiate radiate out more heat than it receives. So Ts will receive radiation that's emitted by the surrounding, and it will emit its own radiation, but it will, because the temperature, because Ts is greater than T surrounding, it will radiate out more heat than it receives, which means that the net heat will leave out of the system, will leave out of the surface. Okay, so there will be a radiation in both directions, but if you look at the net radiation will move out of the system, and we'll look at this mathematically as we move forward. Okay, so let's look at some terminologies and equations related to radiation heat flux. And the first one is irradiation. Now, what do you mean by irradiation? Irradiation is denoted by G, or uppercase G, and the units for it is watt per meter square, and it's defined as the rate at which it's the rate at which radiation is incident upon the surface. Okay, it's the radiation that is incident upon the surface per unit area, obviously, and for all wavelengths, so per unit area over all wavelengths and from all directions. Okay, so say you have a surrounding temperature of T surrounding, and let's say you have a surface which is you have an object, let's say it's a semi-transparent object in this case, and your object is at a um, surface is at a temperature Ts, and let's say the surrounding is there is some radiation from the surrounding that is incident, and that radiation is G. So now what will happen is that because this medium is semi-transparent, there will be a portion of radiation, let's use a different color, that will be reflected. Okay, and there will be a portion of radiation that will be transmitted, and a portion of radiation and a part of G that will be absorbed. Okay, so what we do is, we let's say we denote this as G reflected, we denote this as G transmitted, and let's say this is G absorbed. Now your energy has to be conserved, so your G will be equal to G reflected plus G absorbed plus G transmitted, right? Yeah, so and what we can do is we can write this in terms of proportions or portions. So let's say uh, rho times G is reflected plus alpha times G is absorbed plus tau times G is transmitted. Now rho, let's say it's rho r. So rho r is called as reflectivity. Alpha is now called as absorptivity, and tau is the transmissivity. Okay, and these depend on the property of the surface or the material that uh, the irradiation is incident on, or the material which is irradiated. Okay, now we have a G on the left hand side, so all the G's cancel out, so we get an equation that 1 is equal to rho r plus alpha plus tau. So the summation of your transmissivity, your absorptivity, and your reflectivity must always be 1. So this is a very important equation to remember when you're doing or when you're dealing with radiation, because in most of the cases you will be given an absorptivity, and then it will be mentioned that your medium is opaque, which means that your transmissivity is 0. So that's another thing to keep in mind. So for opaque surfaces, transmissivity tau is equal to 0, and this must hold true. So if you're just given the absorptivity, you should be able to find the reflectivity of the medium easily by using this equation right here. Okay, so the second definition that we must know is radiosity. Okay, so what is radiosity? Radiosity is the total thermal energy leaving the system. Okay, and it has the same dimensions, units as irradiation. So it's denoted by an uppercase J and has the units of watts per meter square. Okay, so let's understand what your radiosity will be. So let's say this is an opaque medium. Okay, so if this is an opaque medium, this will mean our tau is equal to 0. Okay, so nothing is being transmitted, and let's say that you have a T surrounding, and the surface and the object or the medium or the surface is at a temperature of Ts. Okay, so G is the irradiation, or the uh, yeah, is the irradiation onto the surface, and let's say there is some that is being reflected, and we can denote that by rows of R times G. So rhos of R times G is emitted, and because the surface has its own temperature, it will emit some radiation because of the temperature as well. So E is the radiation that is emitted by the surface. So what will be our total radiosity? What is the total radiation that is leaving the system? It's the radiation that is emitted plus the radiation that is reflected. So it's the summation of emission and reflection. Okay, and that's the net radiation leaving. So we can write, so this is the radiosity, that's the total radiation leaving. So what will be our net radiation? Okay, let's look at the net radiation. Our net radiation will be, so let's say we are looking at Q rad net. Our Q rad net will be whatever is coming in minus whatever is going out. So what is coming in? We have G coming in minus J going out, and this will be Q rad net coming in. And if we want Q rad net going out, it will be J minus G, right? So we can write this, we can write J as E plus rho R times G minus G. Okay, so we saw that we have an opaque surface, so our equation will be summation of rho R plus alpha plus 0 equal to 1, or alpha equals to 1 minus rho. So this equation here, you can write the emission that's emitted by radiation as epsilon, that's the emissivity. We've seen this equation in chapter 1. So emission will be epsilon times sigma, that's the Stefan Boltzmann constant, times the fourth power of the surface temperature plus rho R minus 1 times G, and we can write this down as epsilon sigma to ts to the power 4, and from this equation right here we can write rho R minus G as, oh, we don't have an equal to sign. We can write rho R minus G as minus alpha times G. Okay, now if we have a gray body, that means your emissivity will be equal to your absorptivity. So emissivity will be equal to absorptivity, and you can write your Q radiation net as epsilon sigma into Ts to the power 4, and you can write the radiosity or the irradiance as minus alpha times sigma into T surrounding to the power 4, where where your epsilon is your emissivity, your alpha is your absorptivity, and because it's gray body, we'll use alpha equal to sigma, and we can write Q radiation net. So we can write our Q radiation net as epsilon into sigma times ds to the power 4 minus d surrounding to the power 4. And this is the equation for the net radiative heat transfer. It's for a gray body, so your equation will be your emissivity times the Stefan-Boltzmann constant multiplied by the fourth power of the surface temperature minus fourth power of the surrounding temperature.